learning, deep learning.
Okay. Hello, everyone. Welcome to day 2 of Development Denver 2019. Your next talk is Learning Deep Learning with Brooks Builds. This is being streamed live on the internet. It's live on twitch.com. I'm sure there's people tuning in. I think that's it. Brooks writes cool code and streams all the time. He already said that, but here he is.
All right, so thank you for coming. We're gonna get started. We have a super busy schedule today because if you don't know, deep learning functions is not like the super simplest to do. I've spent the last month learning this. That's when I found out that I'm doing this stream here, and so I decided to drop everything else I was doing, learn deep learning, because that's something I really want to learn and start incorporating into just my general programming life. And so I wanted to show off what I learned in the last month. So the goal was to create a game, a pong game, and have a deep learning algorithm play that pong game against a traditional simple AI. Now, nothing is working right now because I have taken our code and sort of gutted it. I've commented all the lines out. Now this is the actual neural network itself. I also have the functions. These functions are empty. So this is going to be the live coding aspect of this, is writing the functions that the deep learning neural network uses for real. Oh, well, that's fun with the mic. All right, I think it will stay up now. Okay, so other things that I have, if you're watching online, I do have a special Twitch highlight extension. If you do bang and line, you can give a line number, whatever file I'm in right then, I'll get a highlight over it. I'm sorry about blasting out with this the sound. All right, so let's go ahead and get started. So what I did to create the game, I'm using P5.js. How many of you have heard of P5.js or processing? A couple people, a few people. So P5.js is a library that was created to make creating games, creating visual aspects of programming really easy and simple. And so everything that I have here in the game side is based upon sort of mathematical ideas of vectors and everything else, which is really a simple way of just saying arrays. So if I say a vector, that's just an array of two things, x and y. We'll get into that a little bit more as I go on. So let's begin with what I have. We'll go into our neural network and we'll start uncommenting these. So the first thing we're going to do is we need to get the data from the server. So this is the server. We need to get the data from the client. The way I have this working is that we have a server running and the client loads the game, and as soon as it refreshes, it sends all this data down and says, okay, train the AI based upon that. Well, what is the data? I actually have this let's see, what was it? It was Paint it was MS Paint. Browser. All right, so this is my favorite way to do like a little bit of whiteboard here. So let's say we have a board like this. The data that I'm using is the height of the board, so like where the top is and where the bottom is. I'm also sending a ball, like where that is, it's the x and y coordinates, and I'm sending the direction. So that's called a velocity. That's the direction and the speed that it's going to be going at. I'm sending the paddle, so the height of the paddle, and also where the paddle is, the x and y coordinates of that. And I'm telling it to be trained properly, you should be telling the game, should it be moving up or down with the paddle? So every frame I'm going to be asking the neural network, what should I be doing? Should you be pressing the up button, the down button, or nothing at all? And in this case, I calculate and send where is the crossing point of the paddle line, so the intercept point, and I send that. So in this case, that line is up here. and I send that to the neural network also and tell it, hey, based upon this, where should you move the paddle? And I don't actually tell it where to move. It figures that out on its own. So we'll be writing those functions to get that done. But these are the inputs that are coming in here. So the training data. And I also have this thing called testing data. And we're going to use that at the end to verify, like, how accurate are we? When should we stop? Next, we move on to something I'll call a weight update limiter. Now, in deep learning terminology, this is actually called the alpha. I'm not exactly, again, I've only been doing this for about a month, so I haven't fully learned the terminology yet. So I don't know exactly why it's called the alpha, but I'm sure that with more learning, I'm gonna find out, and it's gonna be great. So you notice this is a really, really small number, and that's because there's this idea that if I just have it as a big number, it can overcorrect and say, oh, when I update myself to, like, when I was wrong, it can bounce over, and it's sort of like a pendulum that goes back and forth, except instead of eventually settling on zero like real pendulums do, it just gets more and wildly out of shape. So we don't want that. That's why this is a small number. Then we're going to have the number of first predictions. So when I first learned this, I just created a single layer neural network and tried to run it, and nothing worked. It never learned. I then later on learned, by turning a page in the book to the next page, that we need a 2-layer neural network for it to learn at all. And so we're going to take one neural network, and it's going to create a guess, and that guess is going to be the input for the next neural network. So this is the number of first predictions. I don't know if there's a scientific way to determine what this number should be. I just guessed until I got something that worked. So 10, we're going to have 10. Number of inputs. So this is the number of inputs that we're getting from our training data. So I'm just setting this, okay, we're getting a training data, and then that's an object that has an inputs array, or an inputs, an inputs array, and then that's all the training data. So I actually have over 100 training data items. So I created that random ball 100 times, created all the paddles 100 times, and then we're going to loop through all those. Then we move on, how many final outputs? What is our final guess going to look like? It's going to be a single number. That's it. 1 if we want to move up, 0 if we don't want to move at all, and -1 if we want to move the paddle down. That's it. All right, so now we're going to get into the programming part. We need something called weights. Weights is an array of arrays, which is also called a matrix. And that's going to be just a series of random numbers to begin with, but these weights are going to be multiplied by the inputs to create our predictions. So we need a matrix that is 10 rows, so that's for our inputs, and the number of predictions wide. So 10 rows down, and actually, no, wait, it's like 9 rows down because I think we have 9 inputs, and 10 rows wide. Anyways, let's begin. I actually wrote a bunch of tests for this, so that way if I do it wrong, I'll know instantaneously. So, create a random matrix. All right, coding time. We're going to start with, well, creating our matrix. So matrix equals an empty array. Now we want to loop over the vertical side. So that's going to be the number of rows. So I'm going to call this row index equals 0. Row index is less than rows. And then row index equals row index plus 1. I like to give these a lot better names than just like I or A or J, because I get really confused easily, and then everything just goes to hell as if I get like 2 or 3 for loops deep. Okay, so that's going to be going down. Well, we need to create the actual columns now, and that's going to be another array. So new row. Actually, I could just row equals empty array. And now we're going to do a for loop over the columns. So that column index equals 0, column index is less than columns, and column index equals column index plus 1. I learned when I was doing Lua programming to just do this style of incrementing as opposed to the plus plus or the plus equals. I just found it easier for me to read later. It's just a style decision. And now let's actually put our random number inside of row. We want this number to be small, and so we don't want it to be like above 1 or below -1, but we want it to be a mixture of negatives and positives. So I'm just going to do const our random number equals math.random, and if I want it to be between -1 and 1, so we need to bring this to between 0 and 2, so we'll multiply it by 2, and then we'll subtract by 1, and that will give us a number between -1 and 1. And we'll just take row and push the random number in, and at the end of this loop, we can now push into the matrix the row. And at the very end, we'll return the matrix. So, did I do it? Yes, 2 passing. So I've got our create random matrix. My canary test of 5 should be equal 5 is also working. So that's a good sign. Back to our neural network. So this means that we now have a random matrix of, if this is like 5 inputs, what does that mean? Well, we now have something like this, where you have like -1, 0.3, 0.4, and so on all throughout that. And that's what a matrix looks like. We also need a set of weights for the second neural network. Now, I think terminology-wise that each of these networks are really neurons, and then the entire network is both of them together. So our first prediction then feeds into the second prediction, and that is our network. Now, I could be wrong, so if I am wrong, please correct me. All right, so we have these 2 sets of weights. Next up, we want how many iterations are we going to go over the entire set of inputs? Now, this is a slightly large number. Let's see what it is. 1, 2, 3, thousands, 1, 2, 3 millions. 1 million times. Now, I didn't get to 1 million when I ran this. It stopped beforehand, but this is our emergency stopgap, so we don't get an unlimited infinite loop here. So I'm not going to do a while true. We'll go over this in a little bit. So let's actually start the training. So we're going to have a for loop, and so I need to go and find the end. I think that is right here. We're going to loop over all of the training input data. Actually, no, this is going to be over our max iteration. So we have 2 loops here. It's going to be a little bit interesting. I'll get back to this in a second. For each time through all of our training data, we're going to sum up all of the errors for all of those training data. So we have 100 training inputs. We're going to get 100 errors all added together. And that's going to let us know, how good are we? Now we're going to loop through all of the training data individually. So that is here. So for each of our training data array, we're going to get the current inputs. So that's the current array of, where the ball is heading, where the paddle is. And we also need the index for this. And that's just for like what the correct one is going to be. All right, time to get our first prediction. What we're going to do for this is multiply the inputs by the weights. And that's all we're going to do. Now this is going to be something called a dot vector matrix. So what is that? Because these are like mathematical terms. Let's say I have this matrix here, and I have another matrix. It has to be the same size. and I have, like, this is position 1, 2, 3. I'm going to take this one and dot vector matrix. Actually, this isn't a vector. Hold on. Let me just cancel that out. I can undo. It's just like MS Paint. A vector is an array. Discard. So we have like 1, 2, 3, and so on. We're going to take this entire vector, and we're going to get something called a weighted sum with this matrix, which is weird because we would think that it's going to be upon this line here, but it's not. It's actually going to be, like, let's say this is -2 and -3. We're going to get this entire matrix, and we're going to multiply each one. So 1 times -1 is going to be -1, so that's -1. We're going to add that to 2 times -2, so that's -4. Well, so that's now going to be -5. And we're going to do that all the way down. So it's going to be the rows here and the columns here. I have the tests here to also show this with my dot vector matrix. So we're going to take our vector. 1 times 1 is 1, plus 2 times 5 is 10, plus 3 times 9 is 27, and that's going to be 38. All right, are you ready? Let's do this. So dot vector matrix. Okay, so what do we need to do? Well, it's kind of hard because we need the left side. We need the rows. It would be a lot easier if we just kind of changed the matrix so that way each row is what I want it to be. And that's actually something called a transpose. Like, there's a mathematical function for that. So I'm just going to say transposed matrix equals transpose our matrix. And once we have that transposed, now the rows are going to be what we want to dot against. So that becomes a weighted sum between two vectors now to become our output. So that's actually going to be a little bit easier. We can now just map through this vector. So we're going to return matrix.map. We're going to take in the current row, and actually we want the transposed matrix. And we're going to take in the row for this matrix. And we want to get the dot product of the vector and the row. Now this should work, except we don't have transpose written. It's right here. So now we need to do that. All right, so what does transpose mean? Let me come here to the test to show, because I think it'll be a little bit easier to see. A matrix, let's see. Here is the matrix we want to do. If we have a matrix that's two columns with 3 rows, it's going to make that 2 rows, 3 columns. So the 1, 1, 3, 3, 5, 5. So we're just going to take the far left column and make that the first row, and then so on and so forth. So this sort of like tricked me up when I first started learning this. We're going to do const new matrix equals empty array. We're going to loop through the columns first. So for, let's, what is this? This is column index equals 0. Column index is less than matrix. So the first column in a matrix, and that length, and then column index equals column index plus 1. All right. So now we're going through each of the columns, and now we want to go through each row. So in a way, we can just probably map this. So we can just say new matrix dot. So we're going to push in the result of the matrix dot map. So this is now going through each row, but we have the column index for it. So we're going to get the row, and we're going to return the row of position column index. And then return the new matrix. This took me a little bit of time to fully grok when I'm getting there. It's a little bit interesting, and it's something that with a little bit of time we can delegate. Let's see if I did it right. No, okay, I got undefined. What did I do? I expected array 4 of undefines to equal all of these numbers. Worst case scenario, I do have the correct ones I've already written in another branch. So transpose matrix, we're going to map through that. Wait, I'm going to go to the wrong one. We're going to loop through this, the new matrix dot push, the matrix dot map. So the result of mapping through this matrix, we get the row, and we want to return the row of column index, and then return this new matrix. I would think that that should work, but just because I don't want to take too much time, I only have like less than half an hour left. I'm going to switch over and to my master branch and take a really quick look at what I did. Oh, I need to commit these. So building the functions. Work. Win. And stage them. All right, so now let's switch over to master. What did I do wrong? Oh, let's see. So transpose matrix, we're going to loop through the matrix with index, so we're just going through the columns. We're going to get our new row. We're going to for each go and push row matrix with index. I mean, it feels like I should have gotten the same one, but I'd have to look at it a little bit longer. Let's switch back. Oh, that was the dot vector matrix. You know what? I bet it worked. And I looked at the wrong test. All right. What else are we missing? Oh, right. The dot, the actual dot function. We need to write that too. So what is a dot? A dot is a weighted sum where we're going to, well, I already showed that. Let's just do this. So const, it's going to be our weighted sum. Actually, you know what? This is a perfect case for a reduce. So we're going to return vector1 dot reduce. We're going to get our weighted sum, and the next, so it's going to be the vector1 value, and we need the index. So now we want to return the weighted sum plus the result of multiplying the item in vector1 with vector2. So that's going to be our vector1 value times the vector2 of position index. Let's see if I got that. Oh, it got the wrong numbers. Close, but like off by a few. Oh, you know what I also failed to do with a reduce? Just come over a little bit and set the initializer to 0. 6 passing, all right. Let's move on. Back to our neural network. All right, dot vector matrix, that's done. Deactivated first predictions. This is weird. This is how it actually learns. I don't really understand why this works yet. This is gonna, again, more learning for me. We're gonna take these first predictions and multiply them, well, basically just take any negative numbers and turn them into 0. So that way, when we update the weights and we go into the second neural network, the second neuron, it just doesn't make things weird. So it's called a ReLU. I don't also know why it's called a ReLU either. So we're going to go through the vector, and we're going to turn all the negative numbers to 0. So that is a map. So vector.map. We're going to take in the current value. And if that value is greater than 0, return the value. Otherwise, return 0. All right, 7 passing. Then we get our final predictions here. So we're going to do the same thing. We're going to take those inputs from the first neuron, and we're going to multiply them by the weights for the second neuron. And this is going to be our dot vector matrix once again. So we already wrote that code, so we're good. And then now we need to get the difference. Like, how far off were we? We're going to call this the final predictions delta. And what we're going to do is we're going to take the final prediction. It's kind of a matrix right now, so I just need to get the first one. And we're going to subtract from that what it was supposed to be. So training data includes what we should have done, and that's what we're grabbing right here. I somehow accidentally grabbed that and moved it, but I think we're good. Now we want to calculate the error. How much was the error? And we would think this might be the difference, like the delta. The delta is going to be a positive or negative number, depending upon if we missed high or low. The error we don't want to be like is positive or negative. We just want to know, did we miss and how much did we miss by? So we want this to be a positive number. So I'm just going to raise that to the power of 2. This also makes it like really big, which helps us say like, hey, if we're really small with our error, then we're doing good. And now I'm going to increment that total errors with what we got here. So as we go through all of the inputs, we're going to keep track of all of our errors and add them together. So we're going to see, hey, if the errors are getting really, really small, we're getting low errors across all of them, which is a good thing. All right. First prediction delta. So this is another dot vector matrix. So again, this is one of the ones that I don't know if I'd be able to fully explain why this works. Because we're not just subtracting, just like we did with the first deltas, we're doing this dot vector matrix here. So unfortunately, at this point in time, I am going to leave this to, I read it in a book and it worked. So I'm leaving it in here until I learn otherwise. Now we're getting what all the books told me was called the first prediction derivatives. And what that means is I need to get a matrix of ones or zeros. And this is basically going to allow us to turn off some of the, it's not really the inputs, but when we update the weights for, when we update the final weights, we're going to want to make sure we don't update the weights that weren't really providing inputs for the second neural network there. And that's what this ReLU to derivative is. So it's exactly like ReLU, except in one case. Instead of returning the value when it's positive, we're going to return 1 or 0. So return vector.map, we're going to get the value. And if the value is greater than 0, return 1. Otherwise, return 0. More passing tests. I like it. Okay. So this is gonna, in most books you're gonna see these all in one line, and it's gonna be really hard to read. I decided to break these out into multiple lines because then my brain doesn't explode when I read it. All right. Now, deactivated first prediction deltas. What we're gonna do is we're gonna take the first prediction deltas we got, and we're gonna multiply it by these first prediction derivatives to deactivate them. So turn them to 0 if we don't want them to be part of that final weight updates. So this is going to be a matrix multiply. So what is a matrix multiply? That's where we're going to take, let me erase a bunch of this. All right. We're going to take this first item here. So 1, 2, 3. We're going to take this item and multiply it by this item multiply it by this item multiply it by this item, and so on and so forth. So it's simply just each position multiplies by its sibling position in the other matrix, and then we get a new matrix from that. Let's do it. So matrix multiply. Well, this is kind of like a double map here. We're going to go down through, create new vectors. So we're going to return matrix 1 dot map. That's going to give us our matrix 1 row. And do we need the index for this? I'm not sure. If I need to, I'll come back to grab that. This is going to be each row of this. And now we need to multiply each position of this row with this matrix, each position there too. So what do I need? Oh, I do need the index for this. So that's going to be the row index. And now for each vector in here, so that's going to be we're going to return the matrix 1 row dot map, and now we're going to get the column. So it's going to be a value and the column index. And now we're going to multiply this value, so this value times the matrix 2 rows first, so it's the row index, and the column index. Let's see if this giant one line works. Hey, it worked, first time. So I hope none of you are actually trying to like code along with this, because I am moving a little bit fast because I only have 45 minutes. The point of this is I'm trying to inspire you that you can do this too. If you want to go home and watch the VOD and slow it down to like 1/4 speed, that's okay too. All right, our weighted final delta. So by weighting these, what I'm going to do is multiply the inputs. Well, the inputs are going to be the second, like that middle layer, by the final delta. And so this is going to be our dot matrix. Did we have a dot matrix here? Not really, so we have to write this too. So let's come to our functions. And what is a dot matrix? Let's look at our test for this. A dot matrix is we're going to take two matrices of not the same shape. I think that's going to be the most interesting thing here. We have this 1, 2, 3, 4, 5, 6, and then this other matrix, like this. So 1 times 1 plus 2 times 4 is going to be the first item here. So we're going to take two matrices and turn them into a big giant matrix that's the same shape of our weights. Well, if I notice, this is just 1 times 1. This is just a dot between two vectors. So it's exactly what we had before, which is, okay, dot this, the dot with this, up and down. So if we transpose this matrix, we can then dot each vector together, and that's the position of it. All right, so let's do that. So we're going to start with const transposed matrix equals, it was the second matrix we transposed. So transposed matrix 2. Once we have that, we now want to loop through. So essentially map through. We want 3 high, so it's going to be this map through the first matrix and then dot together its row with the new row of the transposed matrix. All right. So we're going to return matrix 1 dot map. We're going to get the, the matrix 1 row and the row index. Okay, so we now want to just dot together. And am I doing this right? I have a feeling I'm not doing this exactly the way I want to. But I'm gonna try this anyway. So I'm gonna dot together the matrix 1 row and the transposed matrix of position row index. Let's see if we're off. We are, okay. So, oh, I got missing parentheses. What did I do wrong here? That opens, this doesn't close. I need to close you. Yeah, so I'm off here. So because I'm sort of lack on time, I'm gonna again go to my sort of backup plan here. We're gonna go to our master branch. More work in progress commits. Whip. How many of you have done this for work when you just whip the commit? All right, doc vector matrix. Where are we? Was it dot vector matrix? Where was I? It was Oh, I lost where I was. I have this slightly different order from here. This was dot matrix. Here's my dot matrix. So we're going to matrix map over the first one. We're going to get the first row. We're going to then transpose in here the matrix 2, map over that. That's what it was, the second map in there. That's what I missed. So let's put this back. So the second map is what makes it bigger and like an array of arrays as opposed to just a single dimensional. I created a vector by accident. Let's make sure that my emergency worked. It did, okay. But we could just totally pretend that I did that right the first time, right? All right, continue on. Our limited weighted final deltas. So now we want to apply that limiter to it and reduce the weighted deltas down. So basically a really tiny number. So when we update the weights, it doesn't update too much. A scalar is a fancy mathematical way of saying just a single number. So we're going to take a single number, which is our weight update limiter, and we're going to multiply it by that entire matrix. So let's go do that. Scalar matrix multiply. All right, so this is going to be our return matrix dot map. So we're going to go down each row. And it might be easier for us to just say our new matrix again equals empty array here. And I might just do this with loops. Okay, so we want to go down the matrix. So we're going to have let row index equals 0, row index is less than our matrix dot length, and row index equals row index plus 1. Okay, so now we're going down each matrix. We want to go across 2, and this is now just going to be it's going to be a map of those vectors. So I can say new matrix dot push, and it's going to be that specific one. So it's going to be our matrix of position row index dot map, and that's going to give our essentially a row. Is it going to be, no, it's actually going to be the value. And we're going to multiply the value, I'll just do the scalar to be in the same order, by the value. And then we're going to return our new matrix. And it worked, perfect. All right, back to here. We have our limited weighted final deltas. We need to do matrix subtract. I am running a bit less on time, so I have 5 minutes left. Tell me, what should I do, audience? Should I continue writing these, or should I switch over to the final one and then show the actual game being played? Switch? All right. So I do have this all online. I can share out the code with you, but I'm just going to switch over to our master. Have to save and whip it. Whip. And I'm going to switch over to Conference Talk Working. I did this all last night. And we're going to start the server. I'm going to show this on the left, and I'm going to bring the game up on the right, and I'm going to hit refresh. So we start seeing the accuracy is going up. This takes over half an hour to train, so I'm not going to wait for that to work. Instead, I'm going to hit my restore weights, which I added in when I realized that it takes over half an hour to train this thing. And last night, I got it to a 98.65% accuracy on those training data. And now we can watch a tournament between our neural network and our simple AI play here. I initially had a 98% accuracy, and the simple AI beat the neural network actually a decent amount. With this one, however, just 0.65% is a significant amount in training, and it's actually able to hold its own a lot better. In fact, the number one way that the that the neural network, or that the simple AI loses, is because of a clipping issue. Because every once in a while, as the ball speeds up, which this is another thing, I added angles that I didn't train the neural network on. So it's not aware that if it hits at a certain angle, the ball will go off at a different angle. It also doesn't know that every time it hits the neural network's paddle, it increases the speed of the ball by 10%. So it actually has to it figures it out. And then problems like that happen as the ball gets a little bit too fast for it. The simple AI can lose by clipping, but otherwise it will just never lose, because if the ball is above the paddle, it just moves up. Otherwise it will move down or stay still. So in a way, it's the cheater. All right, so bets. Who do we think is going to win? The neural network? How about hands? Who for neural network? All right, for simple AI. All right, you all have faith in me. So far, the game is not going that way, though. All right, so I have a couple minutes. Any questions? Questions from the stream is also welcome too. Yes.
What books did you read in particular?
What books did I read in particular? So I picked up the book called Grokking Deep Learning, which is from the same company, not the same author as the Grokking algorithms. I read through 7 chapters of it to get to this far. Also, chapter 6 was kind of a nightmare. So I'm not sure I would recommend the book. How did I come up with the idea of live streaming my learning? So I found out that I wanted to continue my learning. I find that it's really helpful for my growth mindset. And I want to do it after work, but I would come up after work and I would just basically listen to music or watch TV or watch YouTube and just do nothing. And by streaming, I hold other people now hold me accountable. Even if nobody is watching me, there's that idea, somebody might watch me. And so I started streaming myself doing these projects and learning. And that's how I get myself up in the morning to do my learning time. Any other questions? Oh, like the score of the tournament?
What are they playing to?
It's playing to 10, so it's best of 10. So it is sort of like it's 10:45. I've got to get time for CJ to prepare for his stream. What I'm going to do is I'm going to leave this running, but I'm going to disconnect the stream. So anybody up here, I'll just be over here, and you can come up and take a look at it, and we'll see who wins. And you could also ask me any other questions. So with that, thank you for everybody for coming. Thank you everybody on the stream who's watching the stream. I will be live again on Monday morning, Monday, Wednesday, and Friday at 6:45 a.m. Mountain Time if you want to join me live. Otherwise, I have the VODs in case you don't want to wake up that early and just watch me, asynchronously. All right, with that, I'll see you next time, and bye.